Now here's another one. This is we're going to do this one with parallel axis theorem to start with. And I'm just going to walk quickly through it because you've already done this. But we're going to say that this is going to be uniform about the x prime axis. So we're going to call this part one. Let's go ahead and put that in there. We got part one, and then we got parts two, two and two. In other words, they are the same. So I can just put them as part two. The reason they're the same is they're the same distance, and this is the by observation. That's going to be the centroidal axis. All right, so let's look at our calculation. Sum of bh cubed, or the sum of ig plus ad squared, got bh cubed over 12 of part 1. And we got 2 times bh cubed over 12 plus ad squared of 2. So you can walk through that and see all the pieces. That is equal to that. That's the vertical part, and this is the 2 horizontal parts. Now here's kind of interesting. It looks like this value is a whole bunch compared to this value. And indeed it is. And in fact, it looks like if this was smaller, which it could be if it was thinner or something like that, it doesn't really have as much to do with the total stiffness or the total moment of inertia as the outsides. In other words, there is, if I just did this, I would say that 616 over 729 is equal to 84%. In other words, 84% of the stiffness comes from the 2 outside parts, which I think is kind of curious. All right, let's see if we can come up with the same value using the whole minus the wholes. Now, why does the whole minus the wholes count here? Is because this is, they are, again, uniform. Even the wholes are uniform about the x prime axis. So the wholes don't have to be the same hole. They could have 2 holes. So what I did was I said, this is going to be my beam. Then I have the hole, which is the entire outside. Then I'm going to subtract these 2 inside pieces. Those are the holes. So that's going to be minus minus is equal to the ix prime. All right, so I'll just again give you the overview here. You can kind of watch and see what happens. But I have the bh cubed over 12 of the whole. So that's going to be 200 as the base. The total height is 400 cubed divided by 12. Minus each hole, in this case they are 200 minus 100 and minus 50 divided by 2. So it would be 200 minus 50 is 150, and then you have 75 on each side. So that's what that 75 is. The inside dimension here of this hole is 300 divided by 12. You have to cube that, multiply that by 2, subtract it out, and you get the same thing. So I think that's pretty handy to use if it qualifies. It obviously not every shape qualifies for using the whole minus the wholes. Here's another one. This one is just a little bit more complicated, and I've written the entire solution out for you here. So I'm just going to print it in your notes, and you can see and walk through the whole solution if you wish. But basically here you have 4 pieces, and I'm going to label these. How did I do that? I think I labeled these guys 1 and 2, and this part 3. And then this part up here, 4. I believe that's what I did for this table. Forgot to put them on my notes here. But you can walk through this. You should get a y tilde and area and a y tilde area for each one. Find out the y bar. Let's go ahead and sketch that in. So this will be the x prime axis, and then y bar goes up like that. With that, I'll let you walk through the whole solution and just make sure that you understand it. Again, this is in your student notes, but I just wanted to show this to you because it's, again, just a little more complicated because it has 4 pieces, but we're going to do exactly the same thing. Again, we don't really care about what happens about the y-axis or the y, and this is the centroidal y-axis because it's a uniform or mirror image on both sides of the y-axis. Well, here's something I think is especially curious and interesting. We've talked about how the much of the stiffness, much of the moment of inertia comes from the outside or the extremes of a given cross-section. Let's just look and see how much we reduce the stiffness by drilling a hole in this structure. In other words, here we have a rectangular cross-section. We're going to drill a hole in it and see how much we reduce the stiffness by. How much have we affected the performance of our structure? And really, when it comes right down to this, we're talking about performance in a building application or a construction application or something like that. What we really want is to have something that functions well, has great stiffness if that's what we're looking for, and we want to use the smallest amount of material we can, or we want to be able to run conduit or pipes or wires or something through the structure, and how much are we affecting the performance if we drill some holes in it. So let's just see. I'm going to drill a fairly big hole here and see how much it changes. So I'm going to use the hole minus the hole technique by saying I have the hole, which is BH cubed over 12 of the entire structure. And I'm going to subtract the HOLE, which is a circle. And I found that formula in the back of the book. So in the back of the book are formulas for many different types of shapes, different kinds of standard shapes, and you can look there if you need to get the moment of inertia of something other than a rectangle. We're going to memorize BH cubed over 12 because that's easy. All the rest of them you can look in the back of the book if you need to, or I'll give those to you on an exam if I do that. So again, in homework problems, you might have to look and find the moment of inertia of a different shape. All right, let's see what we've got. This is going to be equal to the base, which is 100. Times 150 cubed minus this circle, which is pi, 25 to the 4th over 4. And I'm going to just put the numbers here. 28.1 e to the 6th minus 307 e3. Then the total is going to be equal to 27.82. Now, if our question was, how much is the stiffness reduced by the hole in the middle? Well, it would be reduced by this much compared to what I started without the hole. So if I were to say this divided by that, I could get a picture of how much the stiffness is reduced. So I'm going to say reduced by 307 E3 over 28.1 E6, and I get that as 1%. In other words, I drilled a fairly significant hole and I reduced the stiffness by only 1%. So very, very little effect happens when you drill. And what we'll see in the next slide is a fairly big hole in something, and we can have still grid. So let's look at this. This is a 2 by 10, a piece of wood. And instead of drilling a hole down through the middle this way, going in this way, I'm going to drill a hole crossways like this. Now you say, is that legal? I still get all this material around here, but if you look at the cross section, which is right here, this is going to be the critical cross section. So I can draw a picture of the cross section when that's all we're doing anyway. And I'm just going to say, here's my new cross section where this is now solid and this is empty right in here. So I can do the same kind of thing. I can find out how much it's reduced by looking at the before and after, or before and the hole. So I'm going to use the hole minus the hole technique again. Again, this is going to be my x prime axis. So I about x prime is equal to BH cubed over 12 of the hole. In this case, I'm going to use a rectangle because at the cross section, if you want to think about this, at the cross section, this can be viewed right here as a rectangle. In other words, there's going to be a rectangular, let me just kind of draw it in here. There's kind of a rectangular cross section of the hole like that. So I'm just going to say BH cubed over 12 of that, of the hole. All right, let's see what I've got. This is a 2 by 10, so this is 2, and this is 10 high. So this would be 2 times 10, and this is inches, cubed over 12. minus, in this case, still the base is 2, 6 cubed over 12. And let's scooch this up just a little bit. So that's going to be equal to 166.6 minus 36, which is equal to 130.67. So again, if we want to know how much it has reduced, I would say that this would be reduction is going to be equal to 36 over 166, which is about 22%. So again, not a 21% maybe. It's not very much, considering I've taken out a whole bunch of material. And so in construction techniques, you'll find that carpenters and other kinds of construction professionals will drill great big holes in pieces of wood, and it doesn't, and they'll run conduit and pipes and all that stuff through and wires through these great big holes in floor joists, and it still has great function, even though you're modifying it in a significant way.